Hi, children and young adults, and a few of you weirdos. Is he talking about me? You better not be talking about me. You better not talking about me. When I do my best Marlon Brando mafia impression, I drink my Dunkin' Donuts coffee, which I clearly haven't had enough of yet. All right, children. Anybody having fun with Z-scores? So happy we're doing Z-scores. My name is Mr. Krause. These videos can be found nicely organized at www.nkinfinity.com. N stands for Newman, K stands for Mr. Krause, otherwise known as Mr. Key for today, because I will be your Mr. Answer Key. Now, for those of you who watch my videos on a regular basis, that joke is so freaking old, it's driving me insane. So maybe I should stop using it. I don't know. So let's see here. By the way, if you haven't had time to try these out on your own, you might want to pause the video, do the problem, pause the video, do the problem, instead of watching the monkey perform. But let's see. Here we go. Research indicated that the age in which women have their first child surveyed in a simple random sample of 250 women having at least one child and found an approximate normal. There it is. Approximately normal. That's why we can draw the normal distribution curve. With a mean of 27.3 years and a standard deviation of 5.4. Let me put this on my map here. What do you got? 27.3 with a standard deviation. That does not look like sigma to me. Standard deviation of 5.4. So that'll be true for all of these, but we're going to draw different pictures for all of these. All right. According to the empirical rule, approximately 68% of women are between. So we know the empirical rule states that in a normal distribution, 68.2%, I know it's exactly 68, it's not even exactly 68.2, it's approximately 68.2, are within plus or minus, though, what did I just write there, children, are within one or plus or minus one standard deviation from the mean. So for this one, really all I got to do is take the mean, which is 27.3, and add one standard deviation. And I get 32.7. And then I'm going to take 27.3 and I'm going to subtract 5.4, and I get 21.9. So 68% of the women, so 68% of women are between 21.9 and 32.7 years of age when they have their firstborn child. Okay. 95% of women. So we have the same picture. Picture's not really going to change. I got 27.3. I got my sigma of 5.4. But now I want to do 95%. Now hopefully you remember from our empirical rule, 95% is minus 2 standard deviations and plus 2 standard deviations. So as I go through here, there's what I'm talking about, all of this. So I got to find that range. Well, okay, well, that's basically just the same thing. We're going to take 27. We're going to add 2 standard deviations. And, 27.3. And then we're going to take 27.3, and we're going to subtract 2 standard deviations. And I'm going to peek at my notes because they're my notes. And that takes us to 38.1. Yes. And 16.5. Ooh, 16.5. That's rough. So 95% of women are between 16.5 and 38.1 years of age when they have their first child. Finally, we get to this question. It's a little bit more difficult. What percent of women are older than 35? Well, I still have 27.3. I still have my sigma of 5.4. And I want to know when it's 35.35. So I want to know what percent of women are older than 35. You need to learn to draw an accurate picture. Notice what this little note says here. Warning, from now on, I will not draw normal curves for you. Because you need to learn to draw an accurate normal curve, and you need to draw it so that it pertains to the problem. I want older than 35. I want this. Now remember, this whole thing, all of this, is 1. So if I just take 1 and I subtract off this piece right here, so if I take 1 and subtract off that piece that I find, I should get the answer to my question. Well, when I use my table, what I want you to get in the habit of saying, okay, I know that I need that piece, but it's the basic same as this piece here. So we're going to find the left-hand side. This is actually what we're going to find, but it's the same value as this one. And we're going to use the table to find that. But before I can use the table, before I can do anything, just like we learned yesterday, you have to find the Z-score. So the first thing we're going to do is find the Z-score. Let's remind ourselves what that formula is. It's the X, or the value you're looking for. What's am I looking for? The measured value, the value you're looking for, minus the population standard deviation, or population mean, divided by the population standard deviation. Laundry's done. So, this case we're looking for 35. I know my population standard deviation, or population mean, is 27.3, and my standard deviation is 5.4. When I put that into my calculator, I come up with 1.43 standard deviations. Now remember, a Z-score measures the number of standard deviations away from the mean. So I need this page. So I'm going to try to have this page up and ready to go. That's the only page I need. Remember, although we want this, get rid of all the stuff from yesterday. Although we want this side here, this answer and this answer are the same. So we always want this left-hand tail. It's just going to tell us the piece we need, and then you got to figure out what to do with it. So what number am I looking for? And whether or not it's positive or negative really doesn't matter. Oops, that's not what I want. I want to do this. So we want 1.43. So we're going to go look for 1.43. So there's 1.40, 1, 2, and 3. So it's 0.0764. So I go back to my other thing. This area is 0.0764. I want to know, oh, well, that's the answer then. So the probability that Z is greater than or equal to 1.43 standard deviations away from the mean is equal to 0.0764. In other words, 7.64% of women are 35 years or older when they have their first child. All right, there we go. All right, I'll be back. This not drawing normal distribution curves is going to come back to bite me in the behind on these problems, because drawing on this thing is kind of a pain. But I'll do the best I can. If I do it better than you, you're in trouble, because I'm not even looking at the thing I'm writing on. Plus, the thing I'm writing on is here. This is the thing I'm writing on. It's black. You know, it's not like I got lines or distributions or anything. It's just black. Here it is. Just black. So, and I'm not even looking at it. So, whatever. If my drawings look better than yours, you're in trouble. So let's see what we got here. The heights of American men are normally distributed. So that means immediately I can draw a normal distribution curve. So I'll draw my normal distribution curve. Should look something like that. All right, so we were given that we have a mean of 69.1 inches and a standard deviation, put it right here in your drawing, 2.9. So we got a mean of 69.1 inches and a standard deviation of 2.9 inches. About 20, now we're going to be doing things a little bit differently today, kids. Check this out. Now I'm telling you the percentage. About 20% of men are shorter than. All right, so 20% are shorter than. We're looking for the short end of kids. So we want the small end of kids. Now think about it. If this middle is 50%, so 50% are shorter than 69.1, 50% are taller than 69.1. I want the percent. I want the height at which 20% are shorter than. So, I don't know, maybe it's 60 inches, maybe it's 61 inches. I don't know what it is. I do know that it's down here. Now, here's the difference. I don't know this value. In the past, I was able to tell you what that value was. Now we don't know what that value is. That's the thing we're looking for. But what I do know is that when I find it, I'm going to know that 20% is down here. So what is the area under that curve? It's 0.2000. So we need to now go to the chart and find that. So I'm going to start working on converting this z-score. So z is equal to x minus 69.1 all over 2.9. So you'll notice in this one, I'm missing two things. I'm missing the height that I'm looking for, and I'm missing the z-score. I've used this number. There are my formulas already. The only thing I haven't used is this 20%, this 0.20. So here's how this one's going to work. We're going to come back over to our table. Now, we need to find the z-score that gives us 20%. So if I give you the stuff that's on the inside of the normal distribution curve, you need to look on the inside of the table. And we need to look at these numbers, and we need to find the one that is 20%. In other words, we need to find the one that is 0.200. You're not going to find 0.200, but we want to get really, really, really close to 2.00. So I'm gonna grab my yellow thing and I'm gonna see if I can get, let's see, that's 0.1 here. That's not close enough. That's 0.18. That's closer. Oh, there's 0.209, 0.206, 0.203. We're getting closer. 0.205. And so now here's my goal. Which of these is closest? Remember, we're looking for 0.200, 20%. This is 20. This first one is 20.33. This is 20.05%. And this is 19.77%. So if you look at these, that's 20.33%. 20.05, 19.77. This is the big winner right here. So that is going to be the closest I can find to 20%. Now I need the z-score. So in order to find the z-score, I'm going to look over here. Negative 0.88. But I also need to find the other piece. So I'm going to go up. And finally, I'm going to go up here. So this is negative 0.84. Notice this is already the first decimal, right? 0.8, right there. And then when I go up here, this gives me the 0.84. So negative 0.84. So my z-score for this one is negative 0.84. So I'll go back over to my thing. And I said, okay, that's got to be negative 0.84. Now remember, if it's on this side, it's negative. If it's on this side, it's positive. But we're always going to look at that first table. We're not even going to look at that other table. So negative 0.84 is equal to 2.9 x minus 69.1. Now, if you end up with an answer bigger than 69, you know you did something wrong. We need to have an answer like 60 or 61 or 62 or something like that. Well, okay, as usual, we're going to cross multiply. So negative 0.84 times 2.9 equals x minus 69.1. So we're going to grab our calculator, and we're going to do negative 0.84. Oops, not my calculator. Negative 0.84 times 2.9 equals negative 2.436. So negative 2.436 is equal to x minus 69.1. Clearly, I have to add 69.1. So I go plus 69.1, and I end up with 66.664. So x equals 66.664. So did it say rounded? Probably should have rounded. Let's round to the nearest tenth, because that's kind of a normal thing. So I would say that 20% of males are shorter than 66.6. Sorry, that's an oh good. I get to put 7. Round it. 66.7 inches tall. That's 5'6", right? All right, so this one's a little bit different. Kind of the same. The average age of vehicles owned, not leased in the United States on the road is 11.4% with 11.4 years with a standard deviation of 2.6 years. Mr. Hansen tells us his car is on the road longer than 85% of the population. If this is true, how old are the cars when he got rid of them? I was going to get my highlighter ready to say that the age of cars is normally distributed. I didn't put it in there. So that's a problem. I should have put the fact that these are normally distributed. So all the stuff that we're going to be doing are normally distributed. So you can assume that. Unfortunately, I should have written that into the problem. So we're going to write our normal distribution curve. Put the information on the curve. 11.4 years. That's our average. Our standard deviation is 2.6 years. Now, let's see what this problem says, because you need to draw an accurate picture of what's going on. Mr. Hansen says he keeps his car on the road longer than 85% of the population. Now, remember, I'm going to try to tell you this again. This whole thing represents 100%. So 85% is the vast majority of this. So we need to come up with 85%. So that's got to be down in this area down here. Somewhere down here is Mr. Hansen's car ages. We just don't know what it is. But 85% would be all of this. So all of this represents 85%. Now, here's the dilemma. I told you before, we are only going to use the tails. Because trust me when I tell you, once you get used to using just the tails, this process becomes much simpler. And that's all you're going to do next year in our AP Stats is we just use the tails. So I want you to get used to just using the tails. So we only can find tails. We can only find tails. And this is the tail I want. I don't really want that tail. I want this tail. But remember, they're the same. So let's go back. If I can only do tails, I need to actually find this tail. So if this big, huge piece is 85%, then this tail is 15%. So we're only going to use, so when we are looking, we're going to look for 0.1500. So let's set up our equation. Z is equal to X bar, which we don't know, minus the average, which was 11.4, divided by the population standard deviation, which is 2.6. So we need to go find our Z-score. So we'll go back over to our table, and we need to find 0.1500. We need to 0.1500. 0.1500. Now be careful. These ones up here, these are all point zeros. We don't want 0.0. We want 0.1. All right, there's 0.12. There's 0.15. 0.151. Uh-oh. So this is 0.151. This is 14. Okay, so it's probably somewhere here. Now the one on the left is 15.15. The one on the right is 14.92. This is 15 away, 0.15 away. This is 0.08 away. This is going to be the one that's closer. And you need to find the one that's going to be closer. And so let's see what it is. It's negative 1 point. It's negative 1.04. See, notice this is negative 1 point. This is always going to give us our first decimal. This number up here gives us our hundredths place. So you can think about the top being the hundredths place. Hundredths place. So 1.04. So that's going to be my Z value. That's my Z-score. So 1.04 is equal to x minus 11.4 over 2.6. All right, then we just cross multiply, so we'll grab the calculator. 1.04 times 2.6, enter. I get 2.704 equals x minus 11.4. Sorry about that awful penmanship. We'll add 11.4. And I get 14.1. So x equals 14.1. So Mr. Hansen keeps his cars on the road on average, or around 14.1 years when he gets rid of them. All right, let's try another one. You caught me enjoying some coffee. All right, police officers in the United States on average retire after 28 years of service. Oh, I don't know how they even do 28 years of service, especially nowadays, kids. That's a tough job. And thank you very much for all police officers. Your father's a police officer. Go give him a hug and tell him thank you. Mr. Krause says thank you for keeping us safe. With a standard deviation of 2.3 years. Officer Dixon says she will retire so that she is in the top 10% of longevity, which means she wants to stay longer than 90% of the people. So we need to figure out what that is. If the number of years of service are normally distributed, after how many years can she retire? Okay. So she is going to be at the top end. Let's put our information on our normal curve. 28 years is the mean. Standard deviation is 2.3 years. And she wants to be up here at 10% longevity. So 10%. She wants to be in the top 10%. Right? So that's 10%. Or, in other words, it's 0.1000. Now, she's beating 90%. Down here is the 90% of all the people that she's beat. This is the 90%. But I remember, I don't even care about that because I only want the tails anyway. So this is, in fact, the piece that I want. 10%. Let's start our Z-score conversation. Z is equal to X, the observed value, the value that we don't know, minus the population mean all over our standard deviation. So again, our goal is going to be able to find 0.100. Now, if you're like me, I get confused sometimes when I go over to this table. I get a little nuts. I get a lot nuts. I'm looking for 0.100. Remember, we're looking on the inside of the chart. 0.1. Don't go up here and find this number. This is not 0.1. This is not 0.1. This is 0.01. Be very, very careful. As a matter of fact, you'll very seldom be up here unless it's a crazy problem. We're looking for 0.100. Here's 0.10. Here's 0.102. Oh, here, look at this. That's got to be it right there. Look how close I am to 0.100. 10%. So I'm at negative 1.2. This gives me the tens place, and I need to get the hundreds place from up here. That's got to be an 8, right? 8. So that's an 8. So negative 1.28. Let me go back. Wait. I just said negative 1.28, but I'm on the right side, correct? Remember, and I should have talked about this on the last time. I'm on the right side over here. Even though I read negative 1.28, because I'm on the right side, I'm still going to just use positive. Remember, that's going to just tell us about the tail, but it always tells us the tail over here on the negative side. Just don't worry about the negatives. It's you. You got to use your brain. So I know it said negative 1.28, and it was probably a little bit confusing on that last problem. I didn't address that. I should have. It's really 1.28. We want to use, because we are on the right side. We want this big 10% up here. So 1.28 x minus 28. Now again, if your answer doesn't come out to be bigger than 28 years, you did something wrong, because she wants to be better than 90%. So she wants to be on the other side. Now, when I go over my calculator, I'm going to do this all in one fell swoop. Oops. Should probably get to my calculator. So I'm going to do, what was it, 1.28? 1.28 times 2.3, enter. And then I'm going to add the 28 years. So there's my answer, 30.99. Now I'm going to get this number, 2.944. 2.944 equals x minus 28, and then x is equal to 30.944. And so if I round to the nearest tens place, and I should tell you, she'll retire, when she can retire after 30.9 years of service. Now, I guess what I would say is she probably can retire after 31 years of service. And that would put her in the top 90% or in the top 10%. All right. Mr. Kelsey has taken 3 different standardized tests. Oddly enough, he scored an 1100 on every single one of them. Rank his performance on the 3 tests from worst to best. So now we're going to be comparing. And now this is the beauty of Z-scores. This is the beauty of Z-scores. I don't have to create a Z-score I don't have to create a normal distribution curve for this test, and then for this test, and then for this test, and then for that test, and then for this situation. They're all going to use the same exact table, the same exact score. We're trying to find that Z-score. Now, Z-score is the number of standard deviations away from the mean. How far away are you from the mean? The further you are away, the higher the percentage, or the more people you beat. So all we're going to do is convert all of these tests to Z-scores. Z equals, he got an 1100 on all of them, so they're all going to start out with 1100 minus test, this should say test 1. Test 2 is going to say the same thing. Z equals 1100 minus. Test 3 is going to say the same thing. Z equals 1100. Remember, 1100 is our observed value. The only thing that's going to change on these is the information on the particular test. How did people do on that particular test? Oh, on test 1, the average was 1,000 with a standard deviation of 90. Well, if I type that in my calculator, I get 100 over 90, or 1. Oh, I wrote the, I almost put that in there wrong. I'm going to have to do this on my calculator because my answer key's wrong. So 100 divided by 90. And I get 1.11. 1.11, right? Because it's 100. And then this one was 920 divided by 150. Oh, this is a little bit different. When I take 120, so subtract off 920 and divide, I get 1 point. I can't find my black pen. I'm going to change to green. I get 1.20. And when I type in this one has a mean of 1050 and an average standard deviation of 48. So when I type that in, I get 1.04. Now some of you are like, where am I getting these numbers from? Well, I'm taking 1100, I'm subtracting off 920, and I'm dividing by, in the middle case, 150, and I get 1.2. In the last one, I'm taking 1100, I'm subtracting off 1050, and I'm dividing by 48, and I get 1.04. So I don't necessarily need to go look at the table because these are their z-scores. The higher the z-score, remember, if I put these on the normal distribution curve, test 1, remember, this is 0. This is a z-score of 0. So if I put these things over here, a z-score of 1.11 would be right here. So that's test 1. A z-score of 1.2 would be right here. So that's test 2. And a z-score of 1.04 would be somewhere around here. So that's test 3. So how did he do? Which test did he do the best on? He did the best on test 2. Then he did the next best on test 1. And finally on test 3, he did the worst. So there they are, ranked in order, 2, 1, 3. Just based on their z-scores. Now, if you wanted to go look those numbers up, you could, but I think it's pretty clear that based on this, a 1.04, he beat all those people. Well, a 1.11, he beat all the people that 1.04 beat, plus more people. And then finally, this person beat everybody. Make sense? This one's fun. In order to stir up some competition and improve grades, Ms. Newman and Mr. Krause have pitted their classes against each other. Ms. Newman's 6-set classes average was 80% with a standard deviation of 3.1. Mr. Krause's class average was 85% with a standard deviation of 2.25%. Miss Newman's student, Miss Solo, was arguing with Mr. Krause's student, Miss McKeebs, that her score was better in relation to her class. So so how do you compare how a student did in one class with how a student did in the other class? It's the same thing on SATs. The reason we take SATs is so that I can compare a student in New York State to a student in California, to a student in Texas, to a student in New York, Florida, to a student in Nebraska. How do you compare them all? That's why you take the SAT. They are standardized tests that are normalized, which means they can take those scores and put them on a normal distribution and see how you did. That's why you normalize those test scores, and that's why we can compare a student from New York with a student from Nebraska. Well, the same thing's true in my class. Maybe I hit a topic better than Miss Newman did, and my kids did better on it, or maybe we did exactly the same, but my student did a little bit better because she was just so smarter. I don't know. So how do you compare a student from student? We have to figure out and normalize them and put them on z-scores. So let's take a look and see what their z-scores are. So let's say, we'll take Solo first. Miss Solo. We're going to figure out what Miss Solo's z-score is. So z equals, in Miss Newman's class, what did she get? Miss Solo got an 88. That was the observed value for Miss Solo. And we're going to subtract off the average from that class, which was an 80, and we're going to divide by the standard deviation, which was 3.1. So this should be somewhere around 2 point something, right? So 2.22. So 2.22. So her z-score is 2.22. Remember, even though these are going to be on different models, because we're going to get a z-score, we can put them on the same normal distribution curve with the z values. Let's talk about McKeeb's. Let's call McKay. Z-score equals 90 minus 85 divided by 2.25. When I do that, I get a Z-score of, oh wait, I apologize. Let me do the math because I think I labeled these wrong. I think hers is higher than that. So let's do 88 minus 80, enter, divided by 3.1. 2.58, 2.58. So Miss Solo's Z-score is 2.58. 2.58. And Mrs. McKeeves is 2.22. So, just on those numbers, you can stop right there and you can say Miss Solo did better in relation to her class than Miss McKeeves did in relationship to her class. So if you were to rank them, Miss Solo would be on the tops of her class, where Miss McKeeves would still be near the top of the class, but not quite as high. And again, if you need to see this on a Z-score, right? There's 0 Z-scores. This might be 2.22, and this might be 2.58. Now, if you went and looked at those tables, I'm a little bit long here. If you looked at those tables and I looked at a Z-score of 2.22, remember, again, I don't care about the negative or not. So 2.22, 0.12. 1.3% of the kids beat Miss McKee, or Miss, this 2.22, 1.2% of the kids, 1.3% of the kids beat Miss Solo. Now let's go, oh no, Miss McKeeves. Now let's go find Miss Solo, which is 2.58, which is going to be right here. Now remember, that's 0.004. So that means 0.4% of the kids beat Miss Solo. So more than likely, Miss Solo got the highest grade in her class. Probably Miss McKeeve got one of the highest grades because only 1% of the class beat her, but less than 1% of the class beat Miss Solo. So that's what that kind of stuff means. All right, let me pause now. All right, so we got one more comparison. So these are about those big, huge animals, manatees. The average male manatees are approximately normally distributed with a mean weight. Let me get this information down. Manatees. A mu of 650 and a standard deviation of 120. The weights of tigers, the mu is 460. And the standard deviation is 90. A certain male manatee weighed 850 pounds. This manatee would have the same standardized weight in pounds as an adult male tiger weighing what? So the only other information that we have is we have an observed value of a manatee of weighing 850 pounds. So it's 200 pounds more than the normal manatee. So what would that equate to in a tiger? I certainly can't say, oh, well, if this one's 200 pounds more, I'm going to raise the tiger by 200 pounds. Well, raising the tiger by 200 pounds is like half its weight more. This one's only like a third of its weight more. So we got to figure out, if I had an 850 pound male manatee, what would that equate to on a big tiger? I don't know. So the only thing I can do is convert these things to Z-scores. So what we're going to do is we're going to convert this to a Z-score. So we observe that we have a male manatee that weighs 850 pounds. The mean of the population of manatees is 650, and if we divide by the standard deviation of 120, that'll give us a Z-score of, let me just make sure my math is right. It'll be a good way to check my answer key. So 850 minus 650, enter, divided by 120. 1.67. So I get a z-score of 1.67. So if I was looking at the normal distribution curve, and manatees, all of them are going to have so everything for, this is the great thing about z-scores. All z-scores, doesn't matter what dynamic or what distribution you're looking at, they all have some kind of mean score of 0, where that's where the middle is. So they have a z-score of 0, that's where the middle is, that's where all the average of these things are. And I have now a manatee that's down here or up here at 1.67. I want to see that same stretch away from the middle for the tiger. So the tiger then just has to have the same exact z-score. It's not going to be that we're going to get an 850-pound tiger. That's just never going to happen, at least not these kind of tigers. But we know that it has to have the same z-scores. So now we're going to do the tiger z-score. It has to have 1.67 z-score. We don't know the observed value of our tiger, but we know all the other information. We know that it averages 460, and we have a standard deviation of 90. So we're going to cross multiply. So 1.67 times 90, and then we're going to add the 460 pounds. So 610. So x equals 610. So a 610-pound tiger would have the same, would be in the same percentile size as an 850-pound manatee. So if you were to line up the tigers in a row, from lowest weight to highest weight, and then you were to line the manatees up from the lowest weight to the highest weight. So the manatees would be like, here. Let me just do this off the side here. So these would be the manatees. They have an average weight of 650. And we line them all up. So maybe the heaviest is 1,000. Line them all down. Maybe the lowest one, we got a little skinny one, that's 450. I don't know. And then we lined up the tigers. The tigers have a mean weight of 460. We line them up. And maybe the highest tiger would be 700 pounds. And the lowest tiger might be 200 pounds. I don't know. But we know that if we had an 850-pound manatee, it would be in that same percentile score as a 610-pound tiger. In other words, it would beat all of these kids. It would be in this highest percent. And what percent is that? Well, let's go look up 1.67 in our table. Just out of curiosity, 1.67. Now remember, this is going to give us our tail score. So 1.6, that's 8, this is 7. This is 1.67 right there. So 4.75%. Now remember, that's 4.75 in the tail. 4.75. So in other words, these weights of these manatees right here, this is in the 95th percentile. They beat 95% of other manatees or other tigers. That's why we use z-scores, so that you can actually make that comparison. All right. Now let's get a little trickier. I think I exhausted that one. Uh-oh, I'm out. How many problems we got left? 1, 2, 3, 4, 5. All right, we got what to do with the range and how to find the mean. So I got 2 different scenarios left. Range is kind of tricky. So let me give you the idea of the range. Before we even start on a problem, here's my normal distribution curve. All right, there's my normal distribution curve. I'm going to say I want to know from here to here how many people are in this range. So from 50 to 80, whatever the number is, I don't even care. From 50 to 80, I want to know all the numbers. Well, maybe I better do it this way. It'll make more sense. So I want to know from 50 to 80. But remember, the thing we're looking at only gives us the values in the tails. Right? So we can find this number. And we can come over here and find this number. So if I can find this number, whatever this number is here, and I can find this number here, and I know that the whole thing is 100%. If I take 100% and I subtract this, so I get rid of all this, and I subtract off this, then what's left over is the thing I'm looking for. And that's the idea of what we're going to be doing now. Isn't that great? Don't you wish you could erase that fast on your... This is why getting a Microsoft, what are those things called? Surface. Those things are nice because that's how fast you erase. So let's see what we got. We got a survey taken to determine the number of hours per week that nursing students study. The distribution is approximately normal. There it is. I can draw my normal distribution curve, so let's get it in. With a mean of 24 and a standard deviation, get in the habit of writing it right here, of 3 hours. What percent of students studied between 26 and 30? Uh-oh, we got a little bit of an issue on this one. Let me move 26 over so it's a little bit more meaningful. 26. Here. Now, if I just said what percent of kids were higher than 26, wouldn't you go through and find all this? You'd say, oh, I'm going to go through and find all this. But I don't want all the ones that are, all of those. I don't want all of those. I want the ones between 26 and 30. Between 26 and 30. So I don't want all of this. I only want that piece. So that's the piece. Oops, I accidentally got rid of my bottom blue line there. So I don't want all of the ones bigger than 26. I only want the ones in between here. So what I'm going to do is I'm going to find the one for 26. I'm going to find the one for 30. Now, this is all 30. So 30 will give me this percent. 26 will give me this percent. And their difference is what I'm looking for. Sometimes you have to subtract from 100. Sometimes you have to subtract from each other. So this is going to be a tricky one. So let's find their z-scores first. So 26 minus 24 over 3. So that's 2 over 3. So that's going to be 0.67. And the other one is z equals 30 minus 24 over 3. And that's 6 over 3. So that's going to be a z-score of 2. So I need to go find out what those percentages. What percent are greater than or equal to 0.67? And what percent, or what is the probability that my z-score is greater than or equal to 2? So I'm going to go over to my table. I need to find 0.67 first. So again, now I'm not looking for percentages. I'm looking for 0.6987. There's 0.67. 25.14. 0.2514. So 25.14% are bigger than, are studied more than 26 hours. Now let's go find a z-score of 2. It's going to be way up here. That's right here, 2.0. That's 0.0228. That's 2%. Gosh darn it. That's 2%. So this is what did I say? Doggone it. Stop doing that. 0.0228. 0.0228. So again, 26 is 25.14%. More than 26 hours. More than 26 hours. More than 30 hours is 2.28%. And this is the piece I want. So I just need to subtract those two. So I'll come over to my calculator. 0.2514 minus 0.0228. And I get 0.2286. So the answer is 22.86% of students study between 26 and 30 hours. All right, let's try another one. So in the Indy 500, qualifying speeds are approximately normally distributed. There it is. That's important. You got to have that in the problem, unlike that problem earlier that I blame Miss Newman on, which is completely not even remotely her fault, with a mean score of 217 and a standard deviation of 2.3. What percent of drivers average between 213 and 220? So let's see what we got here. This is a different kind of a problem. Here's 213. Here's 220. Now, if you're a betting man or woman, 213 is like almost, what? Almost 2 standard deviations down, and this is almost 1 standard deviation up, so that's hard to say. So, this z-score of 213 is going to give me all of these. This z-score of 220, when I find it, is going to give me all of these. I don't want those. I want in between. So that's why you have to think. You got to use your brain. I want the stuff that's on the inside, not the stuff that's on the outside. So I'm going to be subtracting again. But the first thing, like I said before, you got to find their z-scores. So let's go. 213. This one's going to be negative. Minus 217 over 2.3. It said 3 and wrote 2. That was kind of silly. So, go over the calculator. 213 minus 217, enter, divided by 2.3. Make sure you don't put those all in at one thing, because all it's going to do is divide the 217 by 2.3. And if you end up with some ridiculous answer that's anything like 100, you're wrong. So it should be, somewhere between -3 and 3. Anything else is probably garbage. So negative 1.74. Round it right. Negative 1.74. We need 2 decimals, right? Because we need the hundreds place. It's not good enough for these the tens place. Remember, the top row on that table is hundreds place. Now let's do the z-score of the other one. 220 minus 217 over 2.3. 220 minus 217, enter, divided by 2.3, and I get 1.30. 1.30. So I got to look up those percentages. This is 1.3 z-score. This is negative 1.74. That's probably not drawn right. And I'm going to find out what this percentage is. That's going to be a pretty big percentage. Let's go over to my table. 1.74. 1.70, 1, 2, 3, 4. 0.0409. I meant it's going to be small, by the way. Where the heck am I going? Oh, I know. Jeez. I am losing my mind. So, what am I saying is this, and by the way, this drawing was not very accurate, so let me try to make this a little bit more accurate. So, 213 is kind of like 2 standard deviations down, so 213 is really here. And that number I found was 0.0408. Right? 0.0408 or 09, was it? 0.0409. 0409. Let me get that right. 9. So that's like 4% are down here. 4% are slower than 213. Now let's do the 220, which is at 1.3. Again, it doesn't matter that they're negative. We're going to look up 1.30. Exact. Oh, wait. I don't think it was 1.30. Wasn't it 1.3? What was my z-score? Yeah, it was 1.30. So 1.30 is right there. 0.0968. So this is 0.0968. So this, I guess, is not a accurate drawing either. That's this piece down here. So again, just like I said before, the whole thing is 100. All of this is 100. I want to get rid of this, and I want to get rid of this. So we're going to take 100. Or 1, and we're going to subtract off 0.0409, and we're going to subtract off 0.0968, and that's going to leave me 86.8623. In other words, 86.23% of drivers are between 213 and 220 miles per hour. All right, I think we got one more between. So maybe you should practice this on your own. SAT scores. I forgot even about this problem. So SUNY Geneseo states that most of its applicants score between 1,200 and 1,400 on the math and reading parts of their SAT, and this is probably pretty accurate. The scores of all students are approximately normal. There it is. As soon as I see it, I can draw my normal distribution curve. Get it on there. Get good at it. Stop. Don't draw crappy things. I don't want to have to embarrass anybody in class. With a mean score of 1267 and a standard deviation of 80. What percent of the students are in the range stated earlier? So what percent of students are between 1,200 and 1,400? Well, 1,200 is pretty close. So let's put 1,200 here. And 1,400, that's way over here. That's those crazy smart people. And I said, what's the range in between, right? What percent is in between these range? So I want all of this. Which means I got to find this, get rid of it. I got to find this, get rid of it. Okay? So let's get z-scores. Z equals 1,200 minus 1,267 over, what was my, 80. And if I do this one, just to save a little bit of time, I get negative 0.8375. 8375, but I need only the hundreds place. So I need negative 0.84. Z-score, 1,400 minus 1,267 all over 880. This one I'm going to get 1.66. So I need to figure out what percent of z-scores are less than negative 0.84, and what is the probability that I get a z-score that's greater than or equal to 1.66. 1.66. I should say less than or equal to. So I got to look those scores up. Negative 0.84. 0.84, 0, 1, 2, 3, 4. There it is, 20.05. So 0.2005, 0.2005, that's 20.5%. And the other one was 1.66. It's going to be quite a bit less. Let's see, 0, 1, 2, 3, 4, 5. There it is. 0.0485. And you'll be able to go up here and go, oh, okay, there's the 6. You can also just count. So 0.0485. So 0.0485. Again, though, I want in between. So I have this tail, which is 20.05%, and I have this tail, which is 4.85%, and I'm going to subtract that from 100%. And you need to show this work. 1 minus 0.2005 minus 0.0485. And if I do that, I end up with 0.7510. So 75% or 75.1% of students are between 1,200 and 1,400 students, which leads you to believe that the majority of their kids are between those two scores. All right. And the last step. Let me get rid of this. Okay, and the final last kind of problems that you're going to be responsible for are finding the mean or finding the standard deviation given information about the problem. So let's see what we got here. The scores on the Clerk 2 exam are normally distributed. Stop and draw your curve. If I don't see curves on your homework or your test, you will not get any credit at all. It is utterly useless to try to do these problems without drawing these curves. So don't even bother. They're normally distributed with a mean of, I was given the standard deviation of 110. And I was told that 25.1% of applicants score above 620. Now, whatever this score is, which is a Z-score of 0, 50% score better than this, and 50% score worse than this. Well, I've given you something where there's 25.1% of applicants score above 620. Well, we're in the above part, so I want over here. So it's probably something like right here. This has to be 620. And 25.1%. Now, remember, when I give you the percent on the inside of the inside of the normal distribution curve, you have to look on the inside of the table. So let's see what we don't know. We're going to convert this, all this about Z-scores. Let's convert this to a Z-score. Nope, we don't know X. Wait, we do know X. The observed score is 620. What we're looking for is the mean. So we know 620. We don't know the mean, or the mu, the population standard deviation. What is the mean, right? What is the mean? And we know that the standard deviation is 110. So I'm missing two things. I'm missing my mu and I'm missing my Z-score. So I need to go find my Z-score. And I need to look up 25.1%. Now remember, that's not what you're looking up. You're looking up 0.2510. That's what we got to try to find. So let's go over to our table. Now remember, we're looking on the inside. We're looking for 0.2510. 2510. Let's see. 22, 26, 22, 22, 22, 22, 24, 24, 25, 2514, 2483. Let's see, that's 25.14%. So that's 0.14 away. And this is 24.83. That's 0.17 away. I guess we're going to use this one, the 25.14. So let's see what that is. That is, remember, again, I don't care about the negative right now. I'll deal with that when I get back to my table. I'll get back when I get back to my thing. This is 987. So I guess if you look at the top of the chart, that should say 0.67. There should be a 7 up there. So I come back to my thing and see, okay, I want it over here, so it's got to be positive 0.67. So I go, all right, now I know my Z-score. 0.67 is equal to 620 minus the mean, or the mu, all divided by 110. All right, so let's do the math. 110 times 0.67, enter, 73.7 equals 620 minus mu. So now I got to subtract 620 minus 620. Oops, that's not what I want. I want this minus 620. And I get negative 546, negative 546.3 equals negative mu. So mu is equal to 546.3. So the average on this Clerk 2 test looks like it's 546.3. All right, one last problem. Future Army members have to take what's called an ASVAB. It's a test that all kids joining the military, and if you're going to plan on joining the military, you'll have to take the ASVAB test. I don't remember what it stands for. But it tests you on a bunch of skills, and determining what you get on that determines what kind of a job you can get in the military. If you score very well, like I scored very well on my test, so I went into military intelligence. If you score very poorly, you might be infantry or a cook or something like that. Now, I'm not saying there are a lot of people that scored really, really well but wanted to be a cook or wanted to go into the infantry, and God bless them because they're awesome. And anybody that joins, awesome, love it. But if you don't score high enough, you can't get the other jobs. If you score high, you can get any job you want, pretty much. So let's talk about it. No. Males and females were told that they need to score in the top 15% in order to qualify. Ooh, there it is, military intelligence branch. I forgot what this was about. The average for the test is 110, and the score they need is 128. Find the standard deviation. So did we say they're normally distributed? Another problem I got to fix. This one doesn't say they're normally distributed. They are normally distributed. Anything with this big. All right, so we know what the average is. The average is 110. They need to score 128. They need to score 128, which if they do that will put them in the top 15%. That means only 15% will beat them. By being in the top 15%, that means they beat 85%. But we don't know is our standard deviation. That's our question mark in this case. So let's convert to a z-score. So z equals 110 minus, oh, wait a second, 110 is our mean. Our observed score, the score we're looking at, is 128. So 128 minus 110 divided by sigma, which we don't know. So we're going to go find this z-score. Now remember, 15% is really equal to 0.1500. So this is what we're looking up, which we've already looked up before, but I don't remember what it is. A lot of these things repeat. So 0.1500, wasn't there a 1.50? Oh, it was right here, right? And it wasn't this the closer one? This is 0.08 away. This is 0.15 away. So we're going to use this one, which is negative 1.001234. So negative 1.001234. But remember, we're on the right side, so we want positive. So our z-score is going to be positive. Remember, because we're over here on the right side, we want the positive. 1.04 equals 128. Oh, wait, 128 minus 110 is just 18 over sigma. Cross multiply. So I get 1.04 times sigma is equal to 18. Divide by 1.04. 18 divided by 1.04. I get 17.307, so 17.307. And it's round to the nearest tenth, so sigma is equal to 17.3. So my standard deviation is 17.3. All right, that's it, kids. I know that was a long haul. Please hit the subscribe button, hit the like button. Tell me what you think. Leave a comment if you want. We're going to be doing lots of review on this stuff. This stuff is normally taught in an AP statistics course. It is now being taught in trig course. So it's a lot to handle. You have to practice with this stuff. Draw your diagrams. Put the information on there. Remember the z-score formula. It's not going to be given to you. It's something you have to memorize. Remember it, okay? It's not that difficult to do. All right, kids? Keep working hard. We're almost done. This finishes Chapter 8, review and test. 9 and 10, and we're done. We start reviewing for the final. Oh, my God, it's so exciting.